Hello, and welcome to the fourth and final video of the FP1 chapter Numerical Solutions to Equations. On the screen is a differentiation question, just to prep you for this video. Give this a go if you've got time. To evaluate the derivative at 1, obviously first we need to differentiate this function. And we do that in the usual way. 12x cubed. Remember, square root of x is x to the power half in index form. And 2 over x is 2x to the minus 1 in index form. And the constant differentiates to 0. Now we're ready to evaluate this at x equals 1 by putting 1 into the derivative, which in this case is just 12 minus a half minus 2, which is 9.5. Okay, so far in this chapter we've done locating roots with a change of sign, interval bisection, linear interpolation. Now we've got the Newton-Raphson method to do pretty much the same thing in a different way. This is all about tangents, because in many, but not all, we'll come back to that, in many cases the tangent to a curve at x will cut the x-axis closer to the root. We can find where it happens and repeat the process. So I've taken this out of the textbook because it's a very good picture. Here, x0 is where we're starting, so we start at x0, find the point on the curve, the tangent to the point is in blue here, we find where it crosses the x-axis, here we call that x1, and then we do it again. At x1, the point on the curve, find the tangent, find where that crosses the x-axis, call it x2. And you can see that quite quickly we get very close to the root. This of course relies on you being able to differentiate and find the x-intercept. So I'll very quickly run through where the formula comes from, but on the next screen I'll just quote the formula, and that's what you should remember. So if we take x0 on our function, and we've got f evaluated at x0, that's the y-coordinate, and the x-coordinate obviously is x0, so these are our coordinates, and in general we write the derivative f prime of x. In this specific case, the derivative at x0 is of course written like this. And you know that's everything we need to find the equation of the tangent, because this thing becomes the m in our straight line equation, and then we use the coordinates, which we've got over here, to find the general equation using y minus y1 equals mx minus x1, where perhaps my notation here is going to get in the way. y1 is the coordinate we've got, this thing, and x1 in the general line equation is actually x0 in this case, and x1 over here means something different. So I hope that's not getting in the way here, but when we put this in, we get y, which is f of x, minus the coordinate we're actually using, f evaluated at x0, equals the gradient, which is the derivative evaluated at x0, times x, the general x, minus the coordinate I'm using, x0. And we don't need to worry too much about the fact that this is really horribly general, because what we're trying to do here is show the general formula. All we need to know is that we're looking for the point where this thing crosses the x-axis, which is where the y-coordinate, the general y-coordinate, is a 0. So when this is 0, I need to rearrange to find out what is x. And this will tell me the first approximation, x1. So a quick bit of algebra here. Divide through by the derivative evaluated at x0. And this gives us x1 is equal to x0 minus the function evaluated at x0 divided by the derivative of the function evaluated at x0. And this thing here is called the Newton-Raphson formula. And you don't really need to know all of this. You can just memorize this formula and apply it like an iterative formula. So the first value goes in here, and that'll give us the first approximation. Then we use that first approximation put that into here to find the second approximation, and so on. So here is the Newton-Raphson formula in its iterative form. The next approximation is equal to the current approximation minus the function evaluated at the current approximation divided by the derivative of the function evaluated at the current approximation. And as with the other methods, you just keep doing it until you get the required accuracy. However, there are some things to be careful of with this method, because although it can be, in some cases, much quicker than the other methods, it will not always take you closer to the root. Also, if you start or land on a turning point, then the formula breaks down completely, because you're trying to divide by 0. Quickly talk through these two things. If, for example, you start your approximation trying to find this root here, you start here. Then the tangent here, that's okay, comes down here like this, it'll cut here and go up here. And then, oh, the tangent there is very shallow, it's going to go all the way over here. So you can see a shallow gradient on your tangent is going to take you further away from the root. And then depending on what happens to the graph way up there, we either get closer or we don't. Of course, if we start on this side, then the tangent here, it takes us very close to the root anyway, it cuts about here just next to the root, and then you take the tangent just next to the root, and it gets closer and closer very quickly. So although it can be very good, you've got to be aware that sometimes it will take you away from the root. And I think usually that's pretty obvious, because you'll get numbers that just seem to be blowing up a little bit. This second point is even more obvious, because obviously if you try and divide by 0, your calculator will tell you that you're doing something silly very quickly. For example, if you start on the turning point here, you know that the gradient on a turning point is 0, that's how we find them. But if you've got a gradient of 0, the 0 will appear here in the denominator of the fraction, and that of course is where you're breaking down. But generally speaking, this is quite a good method. So here is quite a chunky example. I've just taken this one completely out of the textbook because it looks so chunky. It's a little bit intimidating, but I want to go through and show that it's not that bad, and it also hits on some of the key points that we've just gone through. So the diagram here shows part of the curve with the equation y equals f of x, where the function is this. So it's a cubic function. The point A with x coordinate p is a turning point or a stationary point, and the equation f of x equals 0 has a root alpha in the interval 1.8 to 1.9. So that must be this one here, the only positive root we can see on the graph. Part A. Explain why x0 equals p is not suitable to use as a first approximation to alpha when applying the Newton-Raphson method to f of x. Okay, this should be easy because it was literally the last thing mentioned on the previous slide. This turning point will have a gradient of 0, and if you put a gradient of 0 into the Newton-Raphson formula, you're trying to divide by 0, which you can't do. So it just won't work. Part B gives us our first approximation x0 equals 2 for alpha, and says apply the Newton-Raphson method twice to f of x to find a second approximation to alpha, giving our answer to 3 decimal places. Which is a slightly strangely worded question, because it's giving us x0 as the first approximation, and it's asking us to find x2 as the second approximation, implying that x1 is not an approximation, just part of your working out. But I think we'll skip over the problems with the language there, and just go ahead and do what it says, apply it twice, giving our answer to 3 decimal places. So to do this, I'm going to need a little bit more space. So here we go. Formula in green at the top, and the function here. So we're going to need to differentiate this. So the derivative is equal to 3x squared plus 4x minus 5. And then the formula, let's have x1 is equal to x0, 2, minus the function evaluated at x0, and the function evaluated at 2 is itself 2. And then we need to divide that by the derivative evaluated at 2, which is 15. Now, one of the common mistakes to make in a question like this comes out of the simple fact that you've got 2 functions here. And it's not unusual for a student to put a value into the wrong function for the wrong bit of the fraction. So just be careful you are using the function for the numerator and the derivative of the function for the denominator. That gives us 28 over 15. So x2 is 28 over 15 minus the function evaluated at 28 over 15, which is a nice long decimal, and I'll just write 0.13 ... here, but I'll keep the full answer when I'm doing the calculation on my calculator. Putting 28 over 15 into the derivative of the function gives a much nicer number, 12.92. So my answer here for x2 is 1.8558, which to 3 decimal places gives me 1.856. The final part of the question says, by considering the change of sign in f of x over an appropriate interval, show that your answer to part B is accurate to 3 decimal places. So to clarify here, we found an answer in part B, and we've written it to 3 decimal places, but that is a second approximation, or arguably a third approximation, but that's no guarantee that this is the root correct to 3 decimal places. If we did another iteration of the formula, it might change to 1.857, for example. So now we're checking that this is indeed a root to 3 decimal places. To do that, we should use the boundaries of this, 1.8555 and 1.8565. And if that shows us a change in sign, then this is correct to 3 decimal places. So that's what we're going to do. We're going to consider 1.8555 function evaluated at this point, and 1.8565. And if we can guarantee it's between these 2 points, then we've guaranteed that 1.856 is accurate for the root to 3 decimal places. Let's have a look. This one gives us a very small negative number, and this one gives us a very small positive answer. And again, here is that key phrase, change of sign. Therefore, x is equal to 1.856 to 3 decimal places has been confirmed. Now there's only one example of this in the textbook, so I've made up another example here, and I'll go through this one as well. Show that root alpha of the equation f of x equals 0, where this is f of x, lies in the interval 0.5 to 1. So this is another change of sign question. We just need to show that this is true. So f evaluated at 0.5 equals minus 12.75 if you put that all on a calculator, and f evaluated at 1 is equal to 1. Change of sign. Therefore the interval is confirmed as 0.5 to 1. Differentiate the function to find the derivative. Sometimes you'll have to do this as a separate part in the question, but obviously it's leading us into the third part where we're going to use that in the formula. So the derivative here, not forgetting that the index form of this is this, gives us 6x squared plus 8x to the minus 3, and the constant term becomes a 0. Part C, using 0.6 as a first approximation to alpha, apply the Newton-Raphson method to obtain a second and third approximation, giving our approximations to 3 decimal place. So I'll call this one x0. So my second and third approximations will be x1 and x2. The function evaluated at 0.6 is a fairly horrible number. So again, I'll just write that and leave the rest on my calculator. And the derivative evaluated at 0.6 is not much better, 39.19 ... And all of that, if you keep the accuracy on your calculator using the store function, should give you 0.7959. Now I need to keep all of that accuracy on my calculator for the next calculation, but it does say give your approximations to 3 decimal places, so for the sake of the question, I'm going to write that as 0.796. But it's very important that you do not use this rounded value in the next calculation. You must keep the accuracy for your calculations. So x2 is equal to 0.7959, and it's great if you can demonstrate that by writing the ... for your examiner to show that you've kept that accuracy, minus this in the function, minus 2.30 ... 19.66 ... And if you do all of that on your calculator, you should get the answer 0.9131 ... to 3 decimal places, 0.913. And here are the two approximations, where this one here is actually reasonably close to the root. The actual root to 3 decimal places is 0.931, so it's not too bad. And that, I hope, is enough for you to have a go at the exercise 3D questions, but also all of the questions in the review exercise for this chapter. And maybe I'll see you for chapter 4.